Right, let us start then. So the first question, multiple choice question, chloroethene is prepared in the presence of a solid catalyst using the equilibrium below. So the important things in this, before we even go to the which option is it, stuff to pick out, it's an endothermic forward reaction from that plus sign. So endothermic is the forward reaction, and we've got 1 mole of gas on the left and we've got 2 moles of gas on the right. So that would be the first thing I would always do at the start of any equilibrium question. So the question now, which change would result in an increased equilibrium yield of chloroethene? So in other words, what is going to push this equilibrium over to the right and give us a higher yield of chloroethene, which is obviously this thing here, isn't it? That stuff there. Right, so would increasing the pressure do that? Remember, high pressure favours the side with the fewest moles. Fewer moles are on this side, so that won't do it. So that's wrong. Increasing the surface area of a catalyst. Remember, catalysts don't change the position of an equilibrium at all, so that's wrong. Increasing the temperature. So increasing temperature favours the endothermic reaction. Well, the endothermic reaction is the forward reaction, so yes, that's going to push this over to the right. So that was the answer, so C. Homogeneous catalyst, again, catalysts have already been mentioned, they don't affect equilibrium positions, so that's why C was the only right answer. Okay, so I think most people got that one right, so well done. Next one, we've got this equilibrium at room temperature and pressure. The equilibrium lies well to the right hand side. Well to the right, that means that Kc is going to be much bigger than 1 basically, okay? So what we're looking for is a big Kc value first of all. So we've got 2 with 10 to the minus 3's on, so that's a small number, isn't it? So it's not A and it's not C. So it could be B and it could be D. So look at what they've done. They've given you exactly the same number, 6.5 times 10 to the 2. The only difference is the units. So obviously you've got to have the right units to get the right answer. So if you think about the Kc expression, I'll explain this in full because it'll be good sort of revision for units. Kc expression for this one would be square brackets N2 times H2O squared over NO squared times H2 squared. So that's the Kc expression. So essentially you've got moles per decimeter cubed on the top, because you've got times 1 times squared, so cubed on the top, over moles per decimeter cubed to the 4 on the bottom, because it's squared times squared. Okay, so that will simplify down to 1 over moles per decimeter cubed, 1 over moles per decimeter cubed, 1 over moles per decimeter cubed. So when you take that up to the top, it becomes mol to the minus 1, dm to the 3, and so it was D. After all of that, the answer was D. Okay, so that's why it was D. Okay, number 3. The equilibrium system is set up below. So there it is there. We've got some more stuff I would pick straight out. So endothermic going forwards from the plus sign. 3 moles of gas on the left, 1 mole of gas on the right. Okay. The equilibrium system is compressed. That means the pressure's increased. What is the effect on the value of Kc and on the amount in moles of CH3OH? Right, so the first thing is constant temperature means that Kc must stay the same. So straight away, A is wrong because it's saying Kc increases, B is wrong because it's saying Kc decreases. So we're left with C or D. So it's the amount in moles. So if you increase the pressure, the equilibrium will favour, or the side will be favoured, will be the one with the fewest moles. So it'll go forwards. So the amount in moles of CH3OH will increase. So the answer was D. Okay. Not everybody got that one right. So that's why it's D for that one. Okay. Hope that made sense. Okay, so we're moving into the first sort of wordy answer. Ammonia can be made from the reaction of nitrogen and hydrogen in the Haber process. So again, I'm going to do the same as before, just get into the habit. So that means that the negative sign means that the forward reaction is exothermic. We've got 4 moles of gas on the left and we've got 2 moles of gas on the right. What effect will increasing the temperature, so increasing the temperature, so Kc will change, okay, have on the composition of the equilibrium mixture and the value of the equilibrium constant. Okay, so we'll bring in a little bit of Le Chatelier's principle, and this is where I think the wording's a little bit not great, because ideally it would have said explain your answer in terms of Le Chatelier's principle, so you know to bring in Le Chatelier's principle in your answer. Or in a question later on in this homework, it should say explain in terms of the equilibrium constant what happens or why this happens. Do you see the difference? So that is why I'm not happy with the wording of these questions, but they were the best I had when I put this together, because specimen paper, yeah? Okay, right. So increasing the temperature is going to favour the reverse reaction, okay? Because the reverse reaction is endothermic. So let's get that in. So increasing temperature favours the reverse, and get in what type of reaction it is, favours the reverse endothermic reaction. What was nice when I was marking your homework was some people had annotated there. So even though they hadn't mentioned endothermic in this part, in the written part, I gave them the mark because they'd actually they'd let me know that they knew what type of reaction they were dealing with. It's better though, obviously, if it goes into your answer, but that's why I do encourage people to annotate these things, because then you're giving the examiner something to look at. So increasing the temperature favours the reverse endothermic reaction. Okay, so what's that going to do on the composition of the equilibrium mixture? Therefore, the concentrations of the reactants will increase and product decrease. Okay, and because of that, Kc will therefore decrease. Okay, and that's because the equilibrium is moving to the left. So I hope that makes sense. Increasing the temperature favours the reverse endothermic reaction. Therefore, the concentration of the reactants will increase because the equilibrium is going more that way, to the left. The products will decrease. So obviously, if you think about the Kc, in a nutshell, Kc is the equilibrium concentration of the products over the reactants. Yeah. So if reactants are going up, think about your fraction, you're getting a bigger denominator and you're getting a lower numerator, the Kc value is actually going to decrease as a result of that. Okay. Right, so part C, the calculation. Now, a couple of people didn't set their homework, didn't set their answer out like I have set out in the notes and on the videos and everything, and it made my job harder to mark it. Okay, obviously if you got it right, then I'm not going to deny you the marks, but an examiner is going to be a bit miffed if they're struggling to find the right answers in your work. Okay, so just if you can, try and set it out nice and clearly for the person marking your work. Okay, right, so I'm going to write out the equilibrium again. So N2 plus 3H2 in equilibrium with 2 NH3s. So what does it say? It says chemists mix together 0.45 moles of nitrogen and 0.45 moles of hydrogen. So the initial, remember the I stands for initial, you can put mol there if you want, initial moles of nitrogen is 0.45, hydrogen also 0.45, therefore there won't be any ammonius right at the very start. So it then says the mixture is heated, allowed to reach equilibrium. At equilibrium, the mixture contains 0.4 moles of nitrogen. So that we'll put a C there for change and we'll put an E there for equilibrium. Remember, these are the moles. So 0.4 moles of nitrogen is left. Okay, so what that's telling you is the nitrogen has dropped by 0.05 moles. Okay, to go from 0.45 down to 0.40, it's dropped by 0.05 moles. Okay, so now we can factor in the mole ratio. So for every mole of nitrogen that reacts, 3 times as many moles of hydrogen is going to react. So that's going to drop by 0.005 times 3, which is 0.15. So that means that at equilibrium there's going to be 0.3 left over, because it started with 0.45 and it goes down to by 0.15. The ammonia will go up by, so remember, this is how many moles of nitrogen are going to react. So ratio 1 to 2, so therefore that's going to go up by 2 times that 0.05, so it's going to go up by 0.1. So therefore at equilibrium there will be 0.1 because you didn't have anything to start with. So that was like the first key bit, that's your ICE calculation. So now it's a KP question. So at this point we're going to work out the total moles. So total moles equals the sum of 0.4, 0.3, 0.1, 0.8. That's how many moles you've got. So your mole fractions now, mole fractions, so mole fractions of nitrogen is going to be 0.4 of a total of 0.8. So that's obviously 0.5. The hydrogen mole fraction, is 0.3 over 0.8. That was 0.375. And the ammonia moles was 0.1 divided by 0.8, and that is 0.125. So remember the check you can do at that point, check they add up to 1, which they do. Okay, so I would always do that. So these should always add up to 1, your mole fractions. If they don't, you've made a mistake, so you can go back and check. So now we've got our mole fractions, we can work out our partial pressures. So that's the total pressure times the mole fraction. So it's 500 total pressure times 0.5, so that's 250. Obviously these are all in kilopascals because the total pressure was in kilopascals. 0.375, I'll just underline that so it stands out. So this is going to be 500 times 0.375, which is 187.5. Just circle that. And the final one is 500 times 0.125, which is, just looking at my answers, 62.5. Okay. And then another check you can do is these should add up to the total pressure, 500, which they do. So there's another little check you can do. So throughout the whole question, you know, you're building up your marks with all these separate sections. So the final thing now is, because it's a KP expression or question, we're going to write the KP. Sorry, I'm right at the bottom here. So that equals the partial pressure. Now remember, when I did this on YouTube, some students were going, my teacher says I don't use brackets. I do use brackets, but remember they've got to be curved. So the partial pressure of ammonia squared over the partial pressure of nitrogen multiplied by the partial pressure of hydrogen cubed. So that equals 62.5 squared over 250 times 187.5 cubed, which is 2.37 times 10 to the minus 6. 2.37 times 10 to the minus 6. And the units, so if we look here at the units, you've got kilopascals squared on the top divided by kilopascals times kilopascals cubed. So essentially you've got kilopascals to the power 4 on the bottom. So you've got kilopascals squared over kilopascals to the power 4, which leaves you with 1 over kilopascals squared, which means that when you take it all up to the top, it's kilopascals to the minus 2. Okay. So hopefully that all follows, makes sense. So just remember those little things you can do along the way of a KP calculation. You can work out make sure your mole fractions add up to 1, make sure your partial pressures add up to the total pressure. And remember the brackets, the type of brackets you have to use in the KP expression. Just don't use square brackets. If you'd rather not put any brackets in at all, that's absolutely fine. So I'll rub them out. If you prefer, I'll tell you what, I'll just do it all again. If you prefer to just not use brackets, I'm happy with that. So it's the partial pressure of NH3 squared, just feels weird to me this, times by the partial pressure of N2 times by the partial pressure of H2 cubed. Okay? Right. It's all quiet in the chat, so I'm just going to keep going. Right, so 5, there isn't a part A, so that was obviously just part B of the exam question I took this from. So question 5 was a KC calculation. So obviously this was like this is an ICE one. It's not the year 12 stuff where you're given the equilibrium concentration. You've got to work them out from the initial and the final equilibrium moles of one of the things, ammonia in this case. Right, so I'm going to do the same again. I'm going to write the whole equation out. I mean, really, I should choose a different equilibrium for this question because they're both based on the Haber process. Anyway, it doesn't matter, does it? So the initial moles of nitrogen was 0.8. Obviously, it's given at 0.800, but for the calculation, I'm not going to bother with those zeros. And we've got 2.4 moles of hydrogen. We've obviously got no ammonia initially. Change equilibrium moles. So what does it say? It says we've got the volume. That's important when it comes to concentration, so I'll just circle that. At equilibrium, 0.36 moles of ammonia has formed. So we know that at equilibrium the moles of ammonia is 0.36. Okay, so that means that that's gone up by 0.36. So to go from 0 to 0.36, it's obviously increased by 0.36. Okay, now we need to use the mole ratio to get the other changes. So 2 moles of that needs 1 mole of that to react, yeah, from the ratio. So how many moles of nitrogen are going to need to react to produce 0.36 moles? That's going to have to drop by half of that, so minus 0.18. And the way I would tackle this, now I've got that, now I've got this, I would just say therefore if 0.18 moles of nitrogen react, 3 times that of hydrogen would react. Okay, that's the easiest way to do it. So that's going to drop by 0.54. The other way you could do it is, you know that 0.36 moles of this has reacted, so the ratio here is 2 to 3, so basically 1.5 times 0.36 is how much hydrogen has to react. Either way you get 0.54 moles is reacted. Okay, so now we've done that, we can work out the equilibrium moles. So this is going to be 0.62 and the hydrogen is going to be 1.86. Okay, so all I've done is gone 0.8 minus 0.18 gives that, 2.4 minus that gives that. Okay, now when I was marking your work I noticed that some people just went straight to Kc from here. But remember, these are moles, they're not concentrations, and we've been given that volume there. So the equilibrium concentrations is what you should have worked out. So remember, concentrations moles over volume, so that should be 0.62 over 5, which is 0.124. This is 1.86 divided by 5, so that's 0.372, and 0.36 over 5 is 0.072. So these are the numbers that are going to go into the Kc calculation. Okay, so now we write the Kc expression. Kc equals, remember these are concentrations, so we need square brackets, NH3 squared, because it's balanced with a 2, over N2 times, not plus, I think I saw a plus in somebody's, H2 cubed. Put your numbers in, so 0.072 squared over 0.124 times by 0.372 cubed, sorry, and that comes out to 3 significant figures. Now it hasn't told you how many significant figures to use, but that's 3 significant figures. That's actually 4, isn't it? But you should always give it to the lowest number of significant figures. So these are 3, that's 4, 3, 3. So I would give it a 3. If in doubt, give it a 3. So it's 0.812. I think a couple of people just put 0.81. So I'm afraid I knocked a mark off for that. Okay. Units. So what have we got on the top? We've got moles per decimeter cubed squared on the top, because the concentration term is squared on the top, the numerator. The denominator will have moles per decimeter cubed to the power 4. Okay, so essentially this cancels down, they get wiped out to 1, that goes down to moles per decimeter cubed squared. So 1 over moles per decimeter cubed squared is what you're left with. So that would be moles to the minus 2 dm to the minus 6 on the bottom. So going up to the top, you're going to get dm to the 6 mol minus 2. Okay. So they're both the calculations, which pretty much were answered very, very well. So well done. So the last bit, the last page, is the sort of what I call the wordy answers. And I said in everybody's feedback that I would be really focusing in on how to answer these. Okay. Right. So the temperature is kept at 300 degrees C. The volume is kept at 5 dm cubed. The chemist predicts that addition of nitrogen, so let's just put some little annotations on here. Addition of nitrogen is going to increase the proportion of hydrogen that reacts. So in other words, what that says is it's going to mean that that equilibrium is going to go to the right. Okay. Now, the mark scheme, even though the question didn't make it clear, the mark scheme wanted students to talk about Kc. All right. How would Kc explain this shift in equilibrium? Okay. So the way really you should have answered this is think about the Kc expression. So Kc equals, sorry, I'm going to have to write this again. I know it was on the other page. NH3 squared over N2 times, H2 cubed. Okay, now temperature's kept at 300 degrees C. So somewhere in your answer, you're going to have to say that Kc the value for Kc has to be maintained. Okay, so let's just put a note on there. Value for Kc must stay the same. Oops, I can't spell today, sorry. Okay, right, so how can we weave all this into a sort of decent answer and get all the marks? Right, so this is what I've said. Adding nitrogen would increase the denominator term in the Kc expression. Okay, if you make this bigger, if you make that bigger, the denominator is obviously going to get bigger. So what would that do to Kc? It would make Kc smaller, wouldn't it? Okay, so let's just put something in words now. So adding N2 would increase denominator term in Kc expression. Okay. Kc would therefore decrease. But because the temperature is the same, Kc has to stay at the value that it was at. Okay, so how will this equilibrium bring about that? Keep Kc the same? Well, if it makes the numerator bigger and lowers the denominator, it can actually get back to the original Kc value, and that's how it does it. So how does it make the denominator smaller, the numerator bigger? It moves to the right, and therefore the hydrogen, the amount of hydrogen that reacts must be more than it was before. Okay, so let's get this into a sensible answer. To restore Kc back to value for temperature, the let's say numerator has to increase and denominator decrease. equilibrium, therefore shifts to the right. More hydrogen reacts, therefore prediction correct. Okay, hope that makes sense. But often, like, these wordier answers are often cause the most problems. The calculations students seem to be able to answer them pretty much without any issues. Maybe make the odd daft little mistake when they but they transfer the wrong moles down or something like that, which I know some people did. But yeah, these wordy ones are the pain. But as long as you know that the fundamentals are, if the temperature stays the same, the Kc has to stay the same. So changing any of the concentrations is going to knock it out of equilibrium. So how does that fraction sort of change to get back to the Kc value for that temperature? Okay. And the last bit, I'm afraid, was, I think one person got this right. Suggest why the chemist is more concerned about increasing the proportion of hydrogen that reacts rather than the proportion of nitrogen reacts. And on everybody's homework, I wrote down it's all about the availability of the reactants. So nitrogen makes up nearly 4/5 of the air, so it's pretty easy to get hold of. So a chemist's not going to be that bothered about wasting nitrogen so much because it's really easy to get hold of. Hydrogen, on the other hand, is really difficult to get hold of. So you've got to electrolyze water, it's not as easy to obtain. So that was the answer, I'm afraid, that was in the mark scheme. So I've written something like that. Nitrogen is readily available from the air whereas hydrogen must be manufactured. And I'll just put in brackets, this wasn't essential, but you could have said, for example, by electrolysis of water. Okay, that was what was in the mark scheme for that one. So there. Okay, final question. Two students set up the equilibrium system below. So it's this is an esterification reaction, which you've probably covered at GCSE. No, it's not actually. It's the hydrolysis of an ester. So this ester here is reacting with water, and you produce an alcohol and a carboxylic acid. It's the reverse of esterification, is what I should have said at the start. The student titrated samples of the equilibrium mixture with sodium hydroxide to determine the concentration of ethanoic acid, this thing here. The student used their values to calculate a value for Kc. The student's values for Kc were different, right? That's really, really important. So what does that mean? If the Kc values are different, therefore the only thing that can cause a change in Kc is the temperature is different. So different temperatures. Which of the reasons could explain why the calculated Kc values were different? Each student carried out their experiment at a different temperature. Yep, that would definitely be a reason why Kc would change. Each student uses a different concentration of NaOH in their titration. That has no effect on Kc. Each student titrate a different volume of equilibrium mixture. Again, that's not going to change the Kc value. The only thing that can change Kc is the temperature on Kc. So the only one was D, wasn't it? So that was the homework.